Okay, so actually we haven't discussed much thing. Okay, we discussed about this transmission line theory. Okay, mainly we have discussed that impedance uh, equation and transmission line impedance equation. Okay, so that is very important. You should be familiar with that one. Okay, and we have discussed some terms. Okay, like the reflection coefficients. Okay, and VSWR, those things we have discussed. Wait a minute, Randimal. Randimal, so maybe you can remember that basically we have discussed these two equations. Okay, these are the voltage and current of a transmission line along the transmission line. Okay, so then after that we have discussed this one, that is the reflection coefficients. Okay, so we have already discussed these things, reflection coefficients, and also with respect to reflection coefficients, we have discussed the VSWR. So, okay, maybe you can remember. Okay, so VSWR is um, VSWR is defined as like this: 1 plus magnitude of this reflection coefficients and 1 minus magnitude of this reflection coefficient, because this reflection coefficients will be a complex value. Okay, so we have discussed these things. Okay, then and I think we have discussed this return loss and um, the terms loss and gain also we have discussed, as I can remember. Okay, so anyway, these are some general terms, so you should be familiar with these things. Okay, if you have any problem, you can ask. Okay, so this is the VSWR, SWR. Okay, definition. Okay, yeah, this transmission line impedance equation. Okay, and then we come to the Smith chart, and still we are in the Smith chart. Okay, so basically we see what is the Smith chart. Okay, so Smith chart is designed by means of the reflection coefficients tau. Okay, so this is so you can see that the tau, the reflection coefficient, is a complex value. Here the polar form is there. Okay, polar form is there. Here it is represented using the polar form. Okay, I hope we can discuss. We have already discussed these things. Okay, so that is why I quickly tell you. These are the this is the polar form of a complex number. Okay, so then the Smith chart is defined using the reflection coefficients. Okay, uh, and and here the x-axis is actually the reflection coefficients imaginary axis, and this y-axis is the reflection coefficients real value. Okay, so based on these values, this Smith chart is developed. We have learned that. Okay, so you no need to keep remember those derivations. Okay, those equation you need no need to keep remember, but yes, y-axis is the uh, reflect imaginary reflection coefficients, and x-axis is the real reflection coefficients. Okay, then uh, so there are two Smith chart actually. Impedance Smith chart, that is this one. Okay, so here we have uh, impedance circles. Okay, impedance circles. Okay, these are impedance circles. These are. impedance circles, okay. And also we can write admittance circles also, okay. So these circles are coming in this way, like this, okay. So if we have combined them together, that is called combined impedance and admittance Smith chart, okay, like this, okay. So you can see that these circles are, this direction circles are, uh, is called the impedance circles, this and these are, okay. These are reactive impedance, these are capacitive impedance circles, okay. And these are admittance circles. Admittance means 1 over Z, okay. 1 over Z, that is admittance. Normally referred in Y, okay. Z is the impedance. 1 over Z is the admittance, okay. This is the admittance, okay. R is the resistor. 1 over R is conductance. So same way, Z is the impedance. 1 over Z is impedance, okay. And if you consider the impedance, impedance is resistive plus, there is a reactive parts, okay. This is we call reactance. So normally 1 over reactance are normally referred as susceptance. Okay. So maybe these words are also somewhat important, okay. So you need to keep remember those things, okay. R is the resistor and 1 over R is the conductance. This is the conductance. Z is the impedance. 1 over Z is the admittance, okay. So this is reactance. 1 over reactance is susceptance, okay. So there are 3 words: resistor, conductance, conductance, impedance, admittance, uh, reactance, susceptance, okay. So maybe you have to familiar with these terms also, okay. So these are admittance circles, 1 over Z circle, okay. Mm, then we have learned we have learned how to use this Smith chart to calculate some parameters related with the transmission line, okay. So this example is enough for that one, okay. So in your assignments or mid-semester exam, this type of 1 or 2 question will come, okay. Same way, okay. So maybe this is the capacitive reactance load. So maybe you will get so this is a inductive reactance load. So maybe you can get a capacitive reactance load or something, okay. Likewise, you will get, okay. So I think you can you can do this question, okay. So here we have to calculate some parameters related with the transmission line, reflected coefficients at the road, reflection coefficients at the input, line input impedance, SWR, and return loss, okay. So these things you should be able to calculate, okay. And also you should have the idea what is return loss, what is standing wave ratio, and input impedance. We have talked these things, okay. Reflection coefficients, okay. So these terms you should understand very well, okay. If you have any problem, you can ask, okay. So we learn Smith chart, how to calculate those parameters, okay. So those are the things we have learned up to now, okay. Uh, so actually, those are the things we have learned up to now. Okay. Very simple things we have learned. Okay. Uh, Transmission line equation we have learned, that is voltage and current equation we have learned. Okay. Then we have learned the reflection coefficients. Okay. Then SWR, return loss, those terms we have learned. Then transimpedance line equation. Okay, that is also we have learned. Okay. Then we have learned how to use. So we have learned what is a Smith chart. We have learned what is a Smith chart. We have learned. Okay. The Smith chart. Okay. Uh, so maybe that is so you should have idea what is this. Okay. That idea is enough. Okay. And very importantly, you have learned how to use a Smith chart to calculate uh, transmission line parameters. Okay, line parameters like reflection coefficients, return loss, SWR, input impedance, those things. Okay, so you should be able to do those things. Okay, so we have learned up to this. Okay, and we have also learned something related with uh, impedance matching. Impedance matching. Okay. Impedance matching. Okay. So now I will ask you one question. Okay. We have learned this. Okay. As I can remember, I have explained what is impedance matching and why we need implement impedance matching. Okay. So can you remember why we need impedance matching? Why we need impedance matching? So we have to learn. And so today we are going to learn this impedance matching. There are some techniques related with the impedance matching. So those techniques we are going to learn. Okay. So today our topic is impedance matching. Okay. Yes. Impedance matching normally used in high frequency uh, equipment for what? To ensure what? Yes, but that is not a complete answer. Yes, yes, that is the answer actually. Okay, we are using impedance matching to minimize the reflection. Very good. Okay, okay. So Randimat, I sometime I notice in your exam paper. Okay, you have a good knowledge about the subject. Okay, but sometimes your answer is not directly related with the question. Okay, so so actually, when we are reading the answer, we can see that you have the idea, okay, but your answer is not directly related with the question, okay. Tilanka madam also told me the same thing, okay. So maybe that is why you get some low marks to the exam, okay, okay. Uh, so maybe anyway, you are performing well, okay, but just pay attention on that also, okay. Try to give the direct answer to the question, okay. Uh, Now I doesn't have. Okay. So if you come, maybe we can find some answer sheet. Okay. So anyway, Okay. Okay. So why we need impedance matching? Okay. Actually, your answer is correct, to reduce the reflection. Okay. So we know that. Okay. We know that if a signal coming through a transmission line to another component. So maybe it may be antenna. Okay. For example, if you have a signal generator, okay. If you have a signal generator, in our labs we have the signal generator. We get the signal from the output of the signal generator, and if you connect it to the antenna, okay. So then antenna will transmit this signal. Okay. So this here you have the signal generator, and here you have the antenna. Okay. So here you have the signal generator. Here you have the antenna. Okay. This is the antenna. So antenna is connected to the signal generator to a transmission line. Practically, we are using, what is the transmission line we are using practically? That is a coaxial cable, no? Yes, coaxial. Okay. So normally we are using coaxial cables. Coaxial cables. Okay. And also here we have a coaxial connector, and here also we have a coaxial connector. Okay. So so if you consider this arrangement, okay. So if this signal generator uh, generator feed a power, feed the power to this transmission line, okay, that power is fed to the antenna also. Okay. So here you are sending a signal through the transmission line to the antenna. Okay. So here certain power will be fed to the line, then certain power will be fed to the antenna. Okay. So we need to give this power as much as possible. Okay. So we need to reduce the loss and keep the power as much as possible. Otherwise, it will be a disadvantage. No, if there is a power loss, it will be a disadvantage. Okay. So you know that this is the signal generator. Okay. This is the signal generator. Signal generator will have a certain impedance. Okay. Internal impedance. Okay. So normally it is referred as Zg. Okay. That is the generator. This is the generator impedance. Generator impedance. That is Zg. Okay. If you consider the signal generator, that signal generator has a certain impedance. Okay. Certain impedance. That is Zg. Okay. And the signal, it is normally emit a sinusoidal wave. Okay. Like this. Okay. And this is our source. This is our source. Okay. So here we have a transmission line like this. Transmission line. Okay. Then this is the transmission line. Okay. This is the transmission line. It also has a specific characteristic impedance. Let's say that is Z0. Okay. So here the source has an impedance that is Zg, and transmission line also has an impedance that is Z0. Okay. Zg and Z0. And here you have a load. Here you have a load. Okay. So this is very much identical to this scenario. Okay. You have the generator, transmission line, your load is the antenna. Okay. Okay. So this antenna also will have input impedance. Okay. So that is ZL. Okay. So it is like this. Okay. So this is complete transmission case. Okay. Transmission case. We have a source, we have a transmission line, and we have a load. Okay. So maybe this generator maybe in practically maybe this is not a generator itself. Okay. For example, that may be a power amplifier. Okay. That may be a power amplifier, and power amplifier give a signal. Okay. So generator give a signal to the power amplifier. Okay. So if you consider this part, signal generator is the generator actually, and the load is the power amplifier. So this is the transmission line. Okay. So then power amplifier will amplify the signal and feed it to the antenna. Okay. So if you consider this communication system, this is the generator because this emit the signal. Actually, it is not a generator, it is a power amplifier. Okay. But if you consider this is specific uh, this is specific section, this is act as the generator because it emit, it is the signal source. If you consider only this part, okay. If you consider the overall part, actually this is the signal generator. Okay. But if you consider this specific part, this is the signal source because it emit the signal, then signal is feed to the antenna, then antenna is the load. Okay. So if you consider this specific section, this is the signal generator and this is the power amplifier. If you consider this section, this is power amplifier, this is antenna. Okay. So this is okay for any section like this. Okay. So in the microwave circuitry, this kind of circuit is there actually. If you consider your phone, okay. If you consider your phone, if you consider the transmitting part, your phone has a microphone. Okay. Microphone. Then the microphone signal is fed to the analog to digital converter. Okay. Then that is fed to a modulator or something. Digital modulation is key. That modulated signal is fed to a power amplifier. Power amplifier, then it is fed to the antenna. Okay. So if you consider this is a simple block diagram, okay, not the detailed one. Okay. But if you consider your phone, okay, at the TX side, this circuit is there. Microphone, analog digital converter, modulator, power amplifier, then antenna. Okay. So microphone to ADC, this is one section. So here the source is the microphone, load is the analog digital converter. If you consider this one, ADC is the source, modulator is the load. Okay. If you consider this one, modulator is the source, power amplifier is the source. Okay. So you can, this can be adapted to any section. Okay. That is what you need to understand. Okay. So this kind of communication section we can find in a microwave circuitry, RF or microwave circuitry. Okay. So that is very important. Okay. So anyway, okay. So it is like that. Okay. Now, what is this signal generator is doing? It emit the signal. Then this transmission line will carry it. Then it feed to the antenna or something. Then the antenna will transmit it. Okay. So that is the normal things. Okay. Now we know that. Okay. We already know that if this impedance, this source impedance is not matched with this impedance, some reflection is there. There is a reflection. Okay, signal reflection. Okay. And if this, so here also signal is going to the antenna. Okay, feed to the antenna. Okay. So at that time also there is a reflection. Here also, if this impedance is not matched to this impedance, another reflection is there. Okay, another reflection is there. Okay. And if you consider this total circuit, if you consider this total circuit, okay, if you consider this total circuit, this circuit, okay, this circuit, load plus this transmission line, okay. So you consider this as a one circuit and source as another circuit, then you can calculate a input impedance here, no? You can calculate the input impedance here, is that in? So how can you calculate this input impedance? Tell me. We have already discussed these things. How can we calculate this input impedance? කොහොමද input impedance එක calculate කරන්නේ? Yes, using the Smith chart and another way. There is another way. Using the Smith chart, you can calculate this input impedance. Okay. Actually, here you have calculated that. Okay. Input impedance. Here, actually, what is here? This input impedance is the exact input impedance. Okay. The total circuit impedance. Okay. So here, okay, according to this one, there is a source. Okay. And source is connected to the transmission line, and it is there is a load. This is the load 40 plus 70J. Okay. So actually, if you consider dipole antenna, as I can remember for a dipole antenna, this kind of uh, impedance is there. Okay. So now you are calculating this input impedance means you are calculating this impedance is a thing. Okay. So you can use the Smith chart, and there is another way to calculate this. Using what? තවත් විදිහක් තියෙනවා ඔක calculate කරන්න. මොකද්ද? Yes, very good. Transmission line impedance equation. Okay. So using the transmission impedance line equation also you can calculate. Okay. So this is an in can be calculated using transmission line impedance equation or Smith chart. Okay. And if this total impedance is not related with this, no, okay, so there is another reflection. There is another reflection. Okay. So this reflection is referred as overall reflection. Overall reflection. These are referred as partial reflection. Okay. These are referred as partial reflection. Okay. So there is a uh, relationship between this overall reflection and partial reflection. So we are not going to talk about these things. Okay. Those things. Okay. But some basic things we should see. Okay. Okay. Now we are doing the matching, impedance matching actually. We are doing this impedance matching, okay, to reduce this reflection, okay. So why we need the impedance matching? When a signal is transferred from one circuits to another circuits, okay, the both circuits, if the impedance of those two circuits are not same, some part of signal will be reflected. Okay. So that is we referred as reflection. Okay. So maybe you can remember that reflection can be can be can be defined as can be find using this impedance. Okay, so let's say that here is ZG and here it is Z naught. Okay, so if you consider this reflection, let's say that is to source. Okay, so here that is the Z naught and this is the ZG. Okay, so you are calculating reflection here in this way. Now, so you can calculate it as Z naught minus ZG divided by Z naught plus ZG. So you can calculate this Z tau S. Okay, and if you consider this tau, okay, so it is related with the load. Okay, so that is normally referred as tau L. Okay, so this tau L can be write as here. So you are calculating this way from ZL to Z naught because transmission line is Z naught. Okay, so ZG, sorry, ZL minus Z naught divided by Z naught plus ZG. Okay, now what is this overall reflection? How we can write this overall reflection? Do you have any idea? Okay. These are, as I told you, these are partial reflection. Okay, these are partial reflections. No. So I will write it here again. Okay. Okay. I will write it here again. Okay.